Okay, hi guys. Right, thank you very much for all those people who have done the assessment for already. Well done, you guys. I've marked them and sent them back to you. For everybody else, and for those people, this is the mark scheme here. I'm going to talk you through the model answers, so please go through your tests and modify anything you got wrong. So let's kick off, shall we? Question 1, this was an area that picked a few people up. So, which of those reactions is exothermic? Exothermic reactions give out heat, so the temperature change is a positive one. So C is the one where it gives out heat energy. Now, question 2, he says, scrolling down the list a little bit, excuse me a second, here we go. This is an energy profile diagram for that reaction there. So what is A? A is the activation energy, the minimum energy particles must collide with in order to react. So most people got that, so well done. How do we know that reaction is exothermic? Because the energy of the products is less than the energy of the reactants. So any variation on the theme of they have more than them will do. Okay, or you could say the change in energy. B is negative. Either or will do for that. I've got a few different answers, all pretty much correct, so well done. Okay, question 3. This is the hydrogen fuel cells question. This confused a few people, but I was really pleased by how many people had a go at this. And if you didn't get it exactly right, you got it mostly right. And if you're doing that, then we're halfway there. So, what do we do first? Well, if you're doing that, first you've got to think about is the 3 steps. What's the energy in? What is the bond energy of the reactants? So, I lay mine out, normally on more lines than this, but I want to get it onto one page. I've got, in the reactants, I've got 2 HH bonds. There's 2 molecules of hydrogens, there's 2 HH bonds, and there's 1 molecule of oxygens, there's 1 O double bond O. So that's 2 times HH plus O double bond O. Then I substitute the numbers for it. So 2 times HH is 2 times 436, plus O double bond O is plus 498, which gives me an answer of 1,370 kilojoules per mole. Right, energy out. That is the energy that's released when the products form the new bonds. What are the products? I've got 2 molecules of water. That means there's 2 OH bonds per molecule, and there's 2 of them, so that's 4 OH bonds in total. So energy out is 4 times OH. What's that? That's 4 times 464, which gives us 1,856 kilojoules per mole. So what's the energy change? Well, the energy change is out minus in. So 1,370 minus 1,856 is minus 486. Minus means it's exothermic. So that's the equation there. That's what you got to do. Where people may have gone wrong with this is just by counting the number of bonds incorrectly. Generally speaking, you're really good at putting the right numbers in. It was just the number of bonds. So if you got that wrong, but you got the rest right, you lose 1 mark. You get what we call error carried forward. You got both of those wrong, but you calculate that right. You got 1 mark because that's error carried forward. Okay. Why is O double bond O stronger than the others? Because it's a double bond. Any variation of that, the bond is stronger, I accepted, but bond enthalpy is to do with strength. You'll understand more about single and double bonds next year when we look at covalent bonding and actually how atoms stick together. Right, C was the question I think that probably confused people the most, and it is worth looking at because it will come up fairly frequently. So, in terms of bond energies, in terms of these numbers, why is hydrogen used as a fuel? Well, it's exothermic. Why is it exothermic? Because the energy released in bond forming is greater than the energy used in bond breaking. So there's the 2 marks. The energy released in bond making is bigger than the energy used in bond breaking. Exothermic reactions are used as fuels. We need the fuel to give out energy, which we can then use for a purpose. So that's the 2 marks there. Long and short of it, that number is bigger than that number. So overall, it's exothermic. Right, D, the test for hydrogen. Really pleased you got this right, because we haven't done it yet, and we won't do it until Module 5. So, well done those people who got this right. Squeaky pop, lit splint. We will come back to this later on. I know we haven't done it yet. Having said that, if we'd been in the lesson and been doing fuel cells, we would have done it then. But sadly, practicals are on hold because we can't distance learn them. Okay, E. Now, this question contained a typo. This is a horrible question, so I've kind of ignored it for people who've done it. Hydrogen, it says, is produced in a fuel cell. No, it's not. Hydrogen is not produced. Hydrogen is used in a fuel cell. It's the fuel. It's what goes in, and it is oxidized. By oxidized, I mean it loses electrons. So, hydrogen is used, or hydrogen is oxidized, or reacted, any variation on a theme there, in a fuel cell. Now that's not part of the question, that's just me modifying the question so it makes sense. So please change your question. If you're going to keep this for notes later, change that question so it actually makes some sense. Hydrogen is not made in a fuel cell. What you can do is you can reverse a fuel cell and make hydrogen, but that's not what the question's talking about. So hydrogen is used in a fuel cell, and it's used at the negative electrode. Remember, going back to fuel cells before, you've got the anode and you've got the cathode. The anode is negative, the cathode is positive. This is the same thing. So hydrogen is used at the negative electrode, and that is called the anode. So most of you got that right, which I'm really pleased by. If you didn't, don't worry about it. The question was wrong. So let's just square that one away. On one of my earlier videos when we looked at this, I did talk about the fact that the negative electrode is the anode, and that's the opposite of what takes place in electrolysis. And the question there is why? Now this is a real detour from what we're doing today, but it's probably worth mentioning briefly. The anode is the electrode where oxidation takes place. That's where electrons are lost from whatever the species is. Hydrogen in a fuel cell is oxidized to form hydrogen ions and electrons. In electrolysis, the anode is in fact the positive electrode, and that's confusing, but that's because in electrolysis we're taking ions and turning them into elements, and to do that the negative ions have to be oxidized, i.e. electrons taken off them to turn them back to the element. So if that confuses you, don't worry about it, because I'm never going to mention it again. But that's why this is different to electrolysis. And if you find that it's different in your revision guide and you're not sure why, there's the reason, but I wouldn't worry about it. F, I was surprised by how few people got this one correct. It's a fuel cell. Everything we've looked at involving cells has been producing an electrical current. So this produces electrical energy. It's all about the fact you've got oxidation on one side and reduction on the other, so you have electrons that need to be able to move from one side of the cell to the other. Exactly the same as happened in the electrochemical cell we looked at a couple of lessons ago. So the electrons can't take the short route, so what do? They take the long route and go down a wire, and as they do that, they do work. They perform useful energy transfers as they go. So electrical energy in a fuel cell. Right, G. Two advantages of using fuel cells rather than batteries in spacecraft. There's lots and lots of reasons. They're very efficient. They are lighter than batteries. They don't need recharging the same way batteries do. They make water, which is a useful, obviously, byproduct if you're an astronaut and you want to have a drink. You could also talk about the fact that they can be reversed in terms of you can use solar power to electrolyze the water into hydrogen and oxygen and then react it backwards. Any variation on those. Most people did a great job of this, so well done. And then we get to H, and nobody got this wrong, so well done everybody. So in this one, this is showing the reaction that takes place. So I've got A, which are my reactants, which are hydrogen and oxygen. I've got C, which are my products, which is water. And then I've got the energy change. If I wanted to make this a better graph, what I could do is put a little bump in here, and that would be the activation energy. That would be the energy required to break them apart first. But we don't need to worry about that. So please modify any answers you got wrong. Give yourself a score. If I've marked it already, great. Otherwise, please email me your score. That'd be fantastic, to the usual address. But on that note, guys, take care of yourselves, and I will speak to you soon.